Hello, in this video we're going to continue our study of trigonometric graphs. Up to this point we focused on sine and cosine. Now we're expanding to the other four trigonometric functions: tangent, cotangent, secant, and cosecant. These functions behave differently because they involve division, which introduces vertical asymptotes and unbounded behavior. So in this video, we'll build on what you already know and extend it to these new graphs. Let's get started. By the end of this lesson, you should be able to identify key features of tangent and cotangent graphs, including their period, domain, asymptotes, and intercepts. You should be able to graph transformations of tangent and cotangent functions by locating asymptotes and key points. Use reciprocal relationships to sketch cosecant and secant functions from sine and cosine. Recognize how maximum and minimum values flip when taking reciprocals. And understand how damped trigonometric functions behave using envelope curves. So why does tan of x have vertical asymptotes? Remember, tangent is defined as tan of x is equal to sine of x over cosine of x. So whenever cosine equals 0, we are dividing by 0, which is undefined. That is exactly where vertical asymptotes occur. Cosine equals 0 at wherever x is equal to pi over 2 plus n times pi. So tangent is defined at those values. Between any two consecutive asymptotes, the graph completes one full cycle. That's why the period of tangent is pi. The graph of tangent consists of repeating S-shaped curves. Each branch increases from negative infinity to positive infinity. It crosses the x-axis at multiples of pi. And it is symmetric about the origin, meaning it is an odd function. To graph a transformed tangent function, we follow a consistent process. First, we find two consecutive asymptotes by setting bx minus c equal to positive and negative pi over 2. We then solve for x. Please note that these asymptotes repeat at every pi over the absolute value of b. Next, find the x-intercept. This is exactly halfway between the asymptotes. We then identify quarter points where the y values are plus and minus a, and finally we sketch the curve and extend the pattern. Let's do an example. Here we are graphing y is equal to 2 tan of x over 3. Here a is equal to 2, which stretches the graph vertically, and b is equal to 1/3, which stretches it horizontally. The period is pi over the absolute value of b, which is equal to 3 pi. Now we find asymptotes by setting the argument equal to negative and positive pi over 2. That means x over 3 is equal to negative pi over 2, which gives us x is equal to negative 3 pi over 2, and x over 3 is equal to pi over 2, which gives us x is equal to 3 pi over 2. The midpoint is 0, so the graph crosses the x-axis at 0, 0. At the quarter points, tangent equals plus and minus 1, and multiplying by 2 gives us y values of negative 2 and 2. These key points define the shape of the graph. Let's reinforce the structure of tangent graphs. The value of a controls direction. If a is positive, the graph rises from left to right, and if a is negative, the graph is reflected and falls instead. The value of b controls a period. The larger b compresses the graph horizontally. A larger b compresses the graph horizontally, while a smaller b stretches it out. And unlike sine and cosine, tangent does not have an amplitude because it is unbounded. So when graphing tangent, we focus on asymptotes and shape rather than maximum and minimum values. Now let's move on to cotangent. Cotangent is defined as cosine of x over sine of x. So it is undefined whenever sine equals 0. That gives us vertical asymptotes at x is equal to n pi. The key difference from tangent is the direction. Between asymptotes, tangent increases, but cotangent decreases. So the structure is similar, but the orientation is reversed. Let's try an example. Here we're graphing y is equal to 3 cotangent of 2x. The period is pi over 2. To find asymptotes, we set 2x equal to 0, which gives us x is equal to 0, and 2x is equal to pi, which gives us x is equal to pi over 2. The midpoint is pi over 4. That is where the graph crosses the x-axis. Since a is bigger than 0, the graph decreases from left to right. So it starts high near the left asymptote, passes through 0 at the midpoint, and drops towards negative infinity near the right asymptote. Now let's go from sine to cosecant. Cosecant is the reciprocal of sine, that is, cosecant of x is 1 over the sine of x. We start by sketching the sine curve. Then we take the reciprocal of each y value. Where the sine equals 0, cosecant is undefined, so we place vertical asymptotes. Where sine is very small, cosecant becomes very large. This creates the curved branches of the graph. Now let's interpret the graph. At each maximum of sine, cosecant has a minimum. And at each minimum of sine, cosecant has a maximum. Between asymptotes, the graph forms U-shaped branches. And importantly, the graph stays outside the interval from -1 to 1. Now secant. Secant is a reciprocal of cosine. That is, secant of x is equal to 1 over cosine. We follow the same idea. Where cosine equals 0, secant is undefined, and we place asymptotes. Since cosine is symmetric about the y-axis, secant is also symmetric about the y-axis. The branches of secant open away from the x-axis, upward when positive and downward when negative. Let's try an example. We begin with the guide curve y is equal to 3 sine of x minus pi over 4. This shows a phase shift and a vertical stretch. We find where the guide curve equals 0 and place asymptotes there. Then we identify the maximum and minimum points. At those points, the cosecant graph touches but does not cross. Then we draw the branches that open away from the x-axis. Let's try another example. Here, y is equal to y is equal to 2 cosecant of x over 2. The period is now 4 pi. So the graph is stretched horizontally. We find where cosine equals 0 to locate asymptotes. At maximum points of cosine, secant has minimum values. And at minimum points of cosine, secant has maximum values. The graph forms branches that open away from the x-axis. Here's a key idea to remember. Secant and cosecant never take values between -1 and 1. This is because they are reciprocals. So the graphs always stay above 1 or below -1. Now we introduce damped trigonometric functions. These are functions where a trig function is multiplied by another function. For example, f of x is equal to g of x times sine of bx. Since sine stays between -1 and 1, the graph stays between negative absolute value of gx and absolute value of g of x. These boundaries are called envelope curves. Let's do an example. In this example, the dampening factor is exponential decay. As x increases, the exponential term approaches 0. So the oscillations get smaller and smaller over time. The graph continues to oscillate but gradually approaches the x-axis. This table compares all 6 trig functions. Pay attention to period, asymptotes, and symmetry. These patterns will help you quickly identify each function. Seeing all 4 graphs together helps reinforce the patterns. You can compare how asymptotes behave and how the shapes differ. Some common mistakes include mixing up asymptotes, confusing periods, and thinking secant or cosecant can cross the x-axis. Remember, they can never equal 0. Now it's your turn. Walk through these problems step by step. Focus on the asymptotes, period, and key points. To wrap up, today we learned tangent and cotangent have period of pi and involve asymptotes. Secant and cosecant are built from reciprocals, and damped functions introduce changing amplitude through envelope curves. Next, we'll study inverse trigonometric functions.